to discuss the verification process for our Colorado fire prediction system, which consisted of a coupled fire atmosphere model. We developed this system in conjunction with the Colorado Center of Excellence for Advanced Technology Aerial Firefighting. Just wanted to show everyone real quick where Colorado is located. It's basically in the interior western part of the United States in the circle there. We have mostly complex mountainous terrain, but there's also some plains to the east as well. And we wanted to develop a whole decision support system around the coupled atmosphere wildland fire environment, or CAWFE model, that would allow our fire responders to be able to run some simulations themselves on fires they're responding to get an idea of where the fire may be moving in the coming hours during their response. It's a whole decision support system, so we have all this input data and all these sort of display systems that the end user will use. But the real focus of our verification was this model. Specifically, the CAWFE model was adapted to the Weather Research and Forecasting, or WRF model, and is a module called WRF Fire. So I keep mentioning that this was a coupled model. Specifically, what that means is a lot of our fire spread models are driven by the atmosphere, the wind conditions, temperature, etc., that'll affect the rate of spread and direction of the fire, along with the fuels and fuel moisture. However, the co-FPS also takes into account how the fire in turn will affect the weather. So instead of parameterizing how the fire's release of heat and water vapor into the atmosphere would then in turn affect wind direction and speed, updrafts, and that sort of thing in the atmosphere, the model actually is coupled so that the fire will directly impact the atmosphere. So I have an example here of a simulation from the WRF Fire, or co-FPS model. This was the Last Chance fire in 2012 in eastern Colorado on the plains that destroyed the town of Last Chance. On the left is the burned area perimeter versus WRF Fire, which is in the blue, and then on the right is just an animation of the smoke concentration released from the fire. In this animation, we see at the beginning how the smoke is rising high in the atmosphere as the fire spreads. And then as we move into the nighttime hours and the boundary layer stabilizes, the smoke sort of lays down and isn't rising as high into the atmosphere anymore. So we can look at the weather portion of the model in the traditional way that we'll be doing verification. However, the wildfire spread portion was a bit of a challenge. When we look at weather, it's modeled worldwide. We're usually on a regular grid, but for our wildfire, we only have case studies. We can't do long 2 to 3 month retrospectives to see how our model is doing, because we only have cases if cases happen, and then co-FPS is only looking at a 13 by 13 kilometer box around the fire. Weather's occurring constantly, whereas the wildfire, it'll happen, and sometimes we can get an idea if there are weather conditions that would support the occurrence of a fire or a really dangerous fire conditions. But until something actually sparks, until that person throws a cigarette out the window or lightning strikes, we don't know that a fire is going to occur. So we don't really have that forewarning, and we don't have, as I mentioned, that continuous set of data to do verification against. Also, when we look at weather, it's observed regularly every 3 hours, every 1 hour at set stations and to specific standards set out by WMO or other organizations. But when we look at the observations of the wildfire, that data is really collected to aid in the real-time response of the first responders, of the firefighters, and of the teams managing that fire. So they're taking observations as they need it to help their crew who are in the airplanes or on the ground. And it's not really with verification of a model in mind or putting observations into a model as we do with weather. This also adds an issue of accessing that data. We have our weather data in regular repositories. Different countries have different repositories, or maybe there's some wider regional repositories that the data is deposited into regularly. It's been quality checked, there's quality check flags on it, and it's in a format that we're comfortable using. But with wildfire, because this is just tactical data for responding to the fire, the data may or may not be saved at all. They might be archived somewhere that is not accessible to a researcher. It can be in any sort of format. I know one issue we had early on in the project was our data said it was in UTC time, but it was actually in local time. And so all our verification of our fires were off by 6 hours. So we had to go back and fix that and cross-check that. So those sorts of errors slip through easily. And then I've even been recommended to go into filing cabinets where some paper reports were saved with data I needed. So it's not as straightforward as it is with weather. So we really had to sit down and say, okay, what data do we have that is in its best quality that we can kind of see how well the system's performing? And one of the main observation sets we had were fire perimeters. On the left is an image from our multi-mission aircraft where they would fly the airplane over the fire, and either somebody would manually draw a fire perimeter based on this data, or one of our colleagues, Amy DeCastro, did work to automatically determine fire perimeters from these videos taken from the aircraft. An example of the fire perimeter on the right, showing the active and the contained boundaries in red and black, respectively. So these were, for looking at the fire spread portion of the model, these were really the most robust data we had. We still might only have them once every 24 hours, once every 48 hours. It's really chaotic, especially in the early response to the fire, just trying to get a handle on what's going on, where people need to be, where is the most dangerous area of this fire that we need to stamp out. So these certainly aren't hourly perimeters or anything like that, but this was really the best data we had. And if you kind of look at what these fire perimeters look like, they almost kind of look like blobs of precipitation. So we approached it as if we were evaluating precipitation accumulations in the model. And one of the main metrics we used were contingency statistics. And here's an example for the 2018 season, the cases we had in Colorado. This is a performance diagram. We have success ratio on the x-axis, which is 1 minus the false alarm rate, and the probability of detection on the y-axis. And the great thing about these diagrams is that take advantage of the relationship between different contingency statistics, so that the curved solid lines are the critical success index and the dashed lines are the bias. And in the end, you really want your forecast up in the upper right. That's going to be your best or closest to perfect forecast. You'll notice that a lot of our 2018 case studies are in the upper left here, which means that the perimeter, the forecast fire spread overlapped well the observed fire spread, but there was also a lot of overprediction, high bias, high false alarm rate. And so that gets us to working with our end users and really taking the time to find out what's important to them. And I'll start with the bottom bullet here. The example, this overprediction we saw in the performance diagram wasn't really of concern to our stakeholders and the personnel working with this product. They were much more interested in what the direction of the fire spread was and if we caught that correctly. One of the issues we ran into in terms of overprediction as well is that it was difficult to take into account any mitigation strategies that our responders were using. So some of the overprediction was a product of the model not performing well, but some of the overprediction was also a product of the mitigation techniques and slowing down the fire or securing a a part of that fire line that we didn't take into account in the model. The model is kind of a worst case scenario where if there's absolutely no response to the fire, how might it spread? But to get this feedback from our users, we had regular stakeholder meetings where we could present through the lifetime of the project, where we could present the progress we were making, some of the scientific advances, as well as the verification metrics and evaluations we did. And we could get feedback from them about how they thought the model was looking, if we were focusing on what they thought we should be focusing on, and get some feedback from them. In addition to just kind of the scientific process of developing the system, the stakeholder feedback was critical in getting observations. So I mentioned that we had a lot of difficulty verifying the model with the fire spread just because it's so hard to get those observations or not knowing where to go. So we could get the kind of feedback of, oh, well, that data you need to verify that is in a filing cabinet, you know, at this post. Let me help you get that paper report. Or you could talk to somebody who was a commander on that fire, and they could say, oh, you know, I saw a pyrocumulus cloud go up at this time, or this was the time when the fire became really unstable. And so from a case study approach, which we had to take because of the nature of the wildfires, we were really able to get excellent observational information from our users. So in addition to informing the process, they also really helped inform where we can find observations for these forecasts. So I did mention that they were more interested not in the size of the fire so much as the direction and speed of the spread. And so in addition to the contingency statistics, one thing we were looking at was trying to adapt verification tools used for meteorological phenomena like precipitation for fire spread. And so one of the tools we looked at was the method for object-based diagnostics and evaluation time domain, or MODE-TD. And a schematic of how the tool works is on the right here, where your X and Y axes would be your spatial latitude, longitude, but your vertical axis is time. And so you can look at the evolution of something like a precipitation system over the course of a model run. And this tool is available as part of the model evaluation tools package at the link on this slide here. Because we saw some similarities between how fire spreads and precipitation spreads, we wanted to look at this. However, an issue we ran into is that this tool required hourly observations. And as I mentioned, we have a lot of trouble getting even one fire perimeter for a model run, let alone one every hour. So one thing that we have started exploring is doing some interpolation between the perimeters we do have, just to get a general sense of how the fire is moving through time. So the example here on the left is the 416 fire from 2018. This was one where we had a higher number of perimeters, which was 4 across 30 hours. And so we took the interpolation of this to get this finer scale assessment, just to try to get a sense of, you know, we could visually look and say, yeah, it looks like the model is capturing the direction and speed of the spread, but we really wanted to get that quantitative estimate. And I really wish I had some sort of numbers to show you, but this work was early in the progress when the project ended, so unfortunately I don't have any numbers, but this was the sort of approach we were looking at taking to quantify that direction and speed spread. So the project is technically over. It was a 5-year project with the state, and the system is deployed operationally. Here's an example of that deployment. This is the interface that the responders and managers were used to working with. And so we adapted the outputs of our model and the running of our model to their display that they were already using. And this is an example of a fire that one of the personnel simulated from this year. He added an ignition point, and then this yellow boundary is the fire spread predicted by the model. And the red boundary is the actual perimeter of the model for that ballot time. So here are some resources if you're interested in learning more about the project, or you're definitely always welcome to email me and I can take some questions as well.
Thank you, Amanda. So we have a question from Brian Golding. The WMO is thinking about whether exchange of hazard and impact data could be promoted with associated standards. Do you think this is possible?
I do think it's possible, and I think it would be extremely useful. How difficult or how long it would take, I'm not sure. It seems very hard to, if you're sitting in the room with folks, everyone's eager to get on the same page, but in terms of what standard you develop, how you implement it, and who's going to follow it, that seems like a bigger challenge. So I think it's possible, but I'm not sure how much work it would take.
Okay, a question from Beth herself here. How is spotting handled in the Colorado fire prediction system? So I guess that's where embers kind of start new fires, I'm guessing. And in the verification, is spotting treated by any differently from the main fire spread region?
That is an excellent question, because that is one of the last things we tackled before the project came to its close. So you're correct, spotting is where embers from the main fire are lifted through the atmosphere, land outside the main fire area, and can start additional fires. And we have a module that was developed as part of CoFPS to handle that. And I'm not sure if it's implemented in the operational or not, though, because it was kind of at the very tail end of the project and it's still being worked on. But it's a parameterization where based on the fuel and the fire behavior and the wind, a certain number of firebrands are lifted and dispersed in the model using, I'm not a modeler, so I might be butchering this, but there's some sort of a trace. You can do a particle trace in the model. And then the end result of that is a likelihood map. And so verification of that is going to be difficult and hasn't been done yet. First of all, just trying to find cases where spotting occurred and you can prove it occurred. And trying to verify a likelihood is a whole different method than trying to do something deterministic or even a probability. So we'll have to do more work trying to verify that. One thing we are looking at, one of our team members was in a fire evacuation area earlier this year, and she had a lot of firebrands falling on her as she was evacuating. So she was coming back and she was kind of taking pictures and collecting and seeing that. So we might be able to use that case because we had someone on the ground actually collecting firebrands. But it's kind of an open-ended question because it will be difficult for sure to verify that.
Okay, a question from Anonymous. What was the frequency of the stakeholder meetings? What was the duration? Who participated?
So I believe we had 2 to 3 stakeholder meetings a year. So it'd be about every 4 to 6 months we had stakeholder meetings through the 5-year project. They were usually an entire afternoon, so kind of 1 p.m. to 5 p.m., so 4 or 5 hours with a break in the middle. And the participants were our project managers from the Center of Excellence who were consistently involved in managing the project. Other folks from the Colorado state level fire community that were interested, regional fire responders often came, and then we also had folks from Colorado's air quality prediction who are meteorologists that were looking at smoke's impact on air quality and predicting that. So I don't think we had any local emergency managers. Barb, please jump in if I'm misrepresenting anything. Barb was on this project as well. But I think that's kind of firefighting community, regional and state level, and then our air quality folks.
There were a few people from the Weather Service, like some of the incident managers as well. I don't remember if you said them.
I didn't, thank you.
Yeah.
The question goes on to say, how did the stakeholder feedback information advance your project?
So I did mention a little in my talk how it helped with the verification part, but in terms of advancing the project as a whole or the scientific development of the project, I believe the stakeholder feedback was pretty integral in what areas of the science we focused on. For example, Beth brought up the spotting module, which I neglected in my presentation, but the development of that module was because of the interest of our stakeholders. They were concerned about spot fires and predicting spot fires. So just that the whole development of the module was influenced by the stakeholder feedback. They also helped us know if we were doing a good job or not, if they were happy with the forecast, or if there was something lacking in the forecast that we needed to address.
Okay, there's a question by Brian Gordon, but I think it relates to Julia's talk largely. So maybe we'll come back to that at the end, if there's going to be time for a general discussion at the end. So does this one from Jonathan Vai, I think I got the name right. Does the Colorado Fire Protection System provide any information on the severity of the fire at a given point, e.g. ground fire, single tree torching, intense crown fire? If so, have you been able to do verification based on after fire assessments of vegetation damage?
So I believe, and Barb, again, feel free to jump in. I believe the main output that has to do with severity of fire would be flame length. And that's another example of a parameter that stakeholder feedback is the reason we included it in our output. We have not been able to go out on a fire and do a post-fire analysis and do any sort of vegetation-based assessment. But we were looking at video from the aircraft and seeing if we could get an idea of the flame length, because sometimes they would zoom in on a single tree, so you had a video of a single tree on fire, and if we could get an idea of how tall those trees were, maybe we could get an idea of that flame length. That didn't go very far. Another thing we did to address intensity is we used the video to try to do some case studies on pyrocumulus, because our stakeholders told us when they see a pyrocumulus cloud form, that gives them an indication that the fire is or will shortly be very unstable. And so that's something that they were concerned about. So we haven't done anything directly addressed in your question, but those are two phenomena we did look at.
And a question from David Hoffman, which I guess could also relate to that previous question, but he's asking, is video footage and photographs from social media used as additional information to estimate the perimeter? So I guess it could also be for intensity and things like this. I assume that information is often posted in real time.
So we haven't used social media for the perimeter. It can be a little difficult because you would need to have some sort of GPS location associated with that video. And sometimes social media does have that and sometimes not. It would be a bit labor intensive for the resources we had. But what we have used social media for was identifying cases. We were looking at impacts like air quality impacts, which people would post on Twitter or Facebook or other social media. And then also looking at evacuations that happened and how it impacted the public, and that helped us choose cases we focused on. We also use social media for identifying pyrocumulus cases.
Okay, thank you. That's all the questions we have here at the moment.
All right. Thank you very much, Amanda. That was really interesting. And as someone living in Australia, pretty relevant to us here as well. So at this stage, we've got just a couple more minutes, about 5 minutes until the end of the session. And so I'd like to invite people, if they've got some more general questions that they'd like to raise, to post anything through the chat, and we'll keep an eye on that and see if there's any more discussion that people would like to have.
So I did mention the one from Brian Goulding. He was saying that your question raises a key issue between warning systems in different countries. So the US Advisory Watch warning system is one way of working. At the other end of the spectrum, the UK warning levels are distinguished by risk, but all are called warnings regardless of lead time. So I guess that sort of relates to this sort of coherent treatment of standards, I guess, associated with it.
Huli, would you be interested in saying a few words about that one? I don't know to what extent the Argentine system was consistent across the country and takes one approach or the other. Any comment?
Yeah, well, I know that, well, hold on a second, please. I know that, well, with the experience of the last year working in the WMO environment, that it is really concerned to each country what they call a warning, what they call an alert, what they call a very short-term forecast. In Argentina, all this, what in some places is called a warning, we call it a short-term forecast. For us, we call a warning, at least in Spanish, which I would say the word is alertas, which is very similar to alert, but we call it a warning. It's the 3-day usual warning. So I think this changed from country to country, right?
Yeah.
Could it be if these warnings are put on social media, then they may start to have some kind of coherence across countries and things? If they're sort of put on Facebook and things like that, people have to know what it kind of means.
Yeah, definitely a weather service should work with a communicational framework in order to explain the public what is a weather warning, what is an alert, what is another kind of weather service. Yes, definitely there should be a communicational framework to accompany this kind of services, because if otherwise people don't understand what's the product and what's the difference between one service and another. Yeah, definitely.
So Meteoalarm and the European EMA and projects through UMetNet and so on must have had to deal with this with all of the European countries. I wonder if there's some things we can learn from their experience. If anybody's got any comments, it would be great to, if you're able to speak, there's only a small number who can do that, but or post something in the chat. Would be interesting to know. Okay, we have a comment from Bob Goldhammer that nomenclature is sometimes the biggest problem. That'll be true. All right, well, it seems like we've come to a pretty good stopping point for today's webinar. I'd like to thank all of the speakers today and also thank Martin for his wonderful support. And I'd like to encourage all of you for, thank all of you for coming today and posting some really good comments and discussion. We'll try and make this available. Certainly the presentations will be made available afterwards and recordings. And you should get an email from Martin in the course of time on how to access these. Don't forget, next week, the webinar is on hazard modeling to be led by the modeling task team. So please do come along if you can. It's similar sort of time as this one. And with that, I'll say thanks again and goodbye. Enjoy the rest of your day, night, morning, whatever it might be. Thank you.